because your force is equal to your pressure times your area. Okay, your area was given in square kilometers. You have to convert that to square meters before you multiply. So 1 square kilometer is equal to 10 to the 6th square meters. For number 2, your pressure is 5.85 times 10 to the 5th pascals. For number 3, the mass is 0.61 kilograms. Mass of the frog.
I got twice that.
0.61.
Oh, because they did.
For number 4, your area is 3,982 square meters.
What is it? What did he say?
I don't know. I didn't get an answer.
For number 5,
I'm saying, what did he say?
your pressure or your force on the spring scale was 17 newtons. The force on the platform scale, the big one underneath, was 31.6 newtons.
We're gonna need to go over that. Okay, dude. What was number 4?
Okay, with this one we had 2 scales. We got a spring scale, okay, which was supporting the mass inside the fluid. How it works? Yes. And then this was sitting on top of a platform scale. Okay, and you have this. So for the spring scale, okay, the spring scale is going to measure the net force. And the net force is going to be the weight minus the buoyant force as the block floats in the liquid. Well, your net force then is going to be your weight, which is the weight of iron, or the density of iron, rho Vg. Okay, this is your buoyant force minus your gravitational force. Well, actually, it's the other way around. This is the gravitational force. So 7,870 times your volume, which is 0.00025 times 9.8. And then your buoyant force would be the density of the oil, which is 916 times 0.00025 times 9.8. So what you get is 19.28, and this is 2.28, so you get 17 newtons. And the 17 newtons would be what we register here. Because the 17 newtons of the spring scale pulling up, plus the 2.28 newtons of the buoyant force pushing up, would equal to the 19.28 of the weight pushing down. And then you'd have equilibrium. Now on the platform scale, okay, what you have is you have multiple weights here. You've got the weight of the oil, you've got the weight of the beaker, okay? You also have the buoyant force. Okay, because the buoyant force is pushing up, well, there's an equal but opposite force, which is pushing down. So that on the platform scale, you're going to have mg plus mg plus your buoyant force. Now for one, it's just the beaker, which is 1 kilogram times 9.8, plus the weight of the oil, which is 2 kilograms times 9.8. And then you're also going to have your buoyant force, which is your 916 times 0.00025 times 9.8. Well, the buoyant force is pushing up on this, so it's pushing down on this. Every force, for every force, there is an equal force in the opposite direction. It just doesn't disappear, no.
You just thought wrong. That's all.
Because the buoyant force is pushing up on the block, then it's pushing down on this scale.
There's the door.
So this gives you 9.8 plus 19, 9.8 plus 19.6 plus 2.28, which comes up as 31.6 newtons. Okay, don't forget the buoyant force. For number 6, I've got something is equal to 0.063 meters, the height. Okay, this is a raft sitting in the water, number 6. How deep is the bottom of the raft below the water? 6.37. The weight of the raft equals the buoyant force of the water. And your buoyant force, or your raft, your volume, you would just list as rho times area times height times G. And you know what the area is given, or you know what, the area is given 5.7 square meters, so then you just solve for your height. For number 7, the physics book, density comes up as 1,020 kilograms per cubic meter. Just force, which is the weight over the area. The pressure when it lays flat is 3.48 times 10 to the second pascals, 348. And when you flip it up on an end and you put it on its spine, because the weight is the same, but the area over which the weight is distributed is so much less, your pressure is higher. You get 2.59 times 10 to the third pascals. When you flip it up on an end. So it's this as opposed to that. For number 8, your velocity is 31.57 meters per second. Okay, when you have an incompressible liquid, okay, the volume stays the same. When you move this incompressible liquid through various containers, the volume per second stays the same. Because the fluid doesn't back up. In other words, if it's moving through, then the amount of volume per second that passes through the system has to be the same no matter where you are in the system.
Pardon the interruption, please pick up.
Okay?
With added commentaries.
Yes. Okay? Alex, call for you.
Yes, that's talking about Half-Life 2. Yes, so we're talking about Half-Life 2. They are.
When you're not
Evil
expecting
company.
calls, then it's usually
Is the homework what you gave me yesterday?
homework, what do we got? May as well just do
You're
the
giving me that look as
packet.
if
We
I'm
won't
an
get
expert
to.
on this. Aperture science is the place where they have the subject at.
Okay, have a good
I've
weekend.
never played through the game, so.
Okay, so whenever you have an incompressible liquid, okay, the volume per second flowing through